Namaste, my friend, and welcome back to NEET Chemistry with Typical Monk. This is Class 5, and today we arrive at the most asked chapter in the whole subject, chemical bonding. Here is a gentle mystery to hold for a moment. Water is bent. Ammonia is a squat little pyramid. Methane is a perfect, symmetric tetrahedron. 3 tiny molecules, 3 completely different shapes, and yet each one is built from the same simple idea. When David first saw these shapes, he asked me, how could anyone possibly know that water bends at an angle just under 105 degrees? And the beautiful answer is, you do not memorize it, you understand it. Today, one idea at a time, we learn how atoms bond, how to draw them on paper, and how a single rule about repelling electron pairs predicts the shape of almost every molecule NEET can ask. Take a slow breath. Let us begin. So what will you carry home from today's class? First, how atoms bond at all, the difference between ionic and covalent bonding, and the octet rule that drives both. Second, how to draw Lewis structures, and how formal charge tells us which drawing is the best one. Third, the heart of the class, VSEPR, how repelling electron pairs quietly decide the shape of a molecule. Fourth, the shapes themselves and their bond angles, from linear all the way to octahedral. And fifth, the NEET drills, assertion and reason, match the column, and the how many are correct format. So everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the deepest question. Why do atoms bond in the first place? Atoms bond to reach a stable noble gas octet, 8 electrons in the outer shell, because that arrangement sits at lower energy, and nature always drifts toward lower energy. A lone atom is restless, a bonded atom is calm. There are 2 great ways to reach that octet. The first is the ionic bond, a complete transfer of electrons, usually from a metal to a non-metal. Think of sodium chloride. Sodium hands 1 electron to chlorine, and both walk away happy, each with a full octet. The second is the covalent bond. Here the atoms do not give and take, they share electron pairs. Nama, this is what holds methane together. And water too. The atoms pull their electrons so that each one feels a complete octet. And here is the honest footnote. The octet rule has exceptions. Some atoms settle with an incomplete octet, like boron in boron trifluoride, and some expand beyond 8, like sulfur in sulfur hexafluoride, or phosphorus in phosphorus pentachloride. Keep these 3 in your pocket. NEET loves to test them. Now that we know why atoms bond, let us learn to draw it on paper. This is the Lewis structure, our way of bookkeeping the electrons. The recipe is simple. Count the total number of valence electrons in the molecule. Place the bonding pairs between the atoms first, and then spend the rest as lone pairs, filling octets until every atom is satisfied. But sometimes, more than one drawing looks valid. So we need a judge, and that judge is formal charge. Formal charge equals the valence electrons of the atom, minus its lone pair electrons, minus half of its bonding electrons. It is simply a fair way of asking, did this atom keep its rightful share of electrons? And the rule for picking the winner is lovely in its simplicity. The best Lewis structure is the one whose formal charges lie closest to 0. Nature prefers the drawing when nobody is carrying a heavy charge. And when several good structures genuinely tie, when the molecule refuses to sit in just one drawing, we call that resonance. We will unwrap resonance fully in Class 6, so simply plant the word for now. Now we reach the idea that quietly runs this entire chapter, BeCl₄, the valence shell electron pair repulsion theory. Look at the diagram as it grows. The whole theory rests on one sentence. The electron pairs around a central atom repel one another, and so they arrange themselves as far apart as they possibly can. 2 pairs push to opposite ends and give 180 degrees. 3 pairs spread to 120 degrees. 4 pairs open out to 109.5 degrees. But not all repulsions are equal. The order to memorize is this. A lone pair pushing on a lone pair repels the hardest, then a lone pair on a bond pair, and gentlest of all is a bond pair on a bond pair. And that unequal push has a direct consequence. Lone pairs, being greedier for space. Compress the bond angles, squeezing the bonded atoms closer together. So here is the whole method in one breath. Count the electron domains around the central atom. That means the bonds plus the lone pairs. And that count alone lets you predict the shape. Let us walk the gallery of shapes, from the simplest to the most crowded. 5 geometries, each with its signature angle. With 2 electron domains, the molecule is linear. Beryllium chloride is the classic example, stretched out at 180 degrees. With 3 domains, we get trigonal planar, a flat triangle, like boron trifluoride, with angles of 120 degrees. With 4 domains, the molecule opens into a tetrahedron. Methane is the perfect example, with angles of 109.5 degrees. With 5 domains, we reach the trigonal bipyramid, phosphorus pentachloride, with a mix of 120 and 90 degrees. And with 6 domains, the shape closes into an octahedron, sulfur hexafluoride, beautifully symmetric, with every angle at 90 degrees. 5 names, 5 angles, learn them as a family, and half the chapter is yours. Now for a single highest yield picture in this chapter, watch what lone pairs do to the shape. Look at the 3 molecules side by side. Here is the crucial thing to notice first. All 3 have 4 electron domains, so all 3 share the same underlying tetrahedral geometry. On paper, they begin as equals. Now methane has 0 lone pairs, nothing couches bonds, so it stays a perfect tetrahedron with a bond angle of 109.5 degrees. Ammonia has 1 lone pair. That single greedy pair presses down on the 3 bonds, pushing them closer, and the molecule becomes pyramidal, with the angle shrinking to 107 degrees. Water has 2 lone pairs. Now 2 greedy pairs squeeze the bonds even harder, and the molecule bends, with the angle falling further to 104.5 degrees. Watch the pattern. As the lone pairs rise from 0 to 1 to 2, the bond angle shrinks step by step. Understand this one picture, and you will never confuse these 3 again. Now sit up straight. These 5 lines are what NEET actually asks year after year. 1. The bond angle order: methane at 109.5 degrees, greater than ammonia at 107 degrees, greater than water at 104.5 degrees. Memorize it cold. 2. More lone pairs mean a smaller bond angle, because each extra lone pair adds extra repulsion that squeezes the bonds. 3. Geometry is not the same as shape. Geometry counts every electron domain. Shape ignores the lone pairs and names only the arrangement of atoms. This distinction is a favorite trap. 4. Learn the expanded octet shapes as a set. Sulfur tetrafluoride is a seesaw, chlorine trifluoride is T-shaped, xenon tetrafluoride is square planar, and xenon difluoride is linear. 5. Carbon dioxide is linear and non-polar at 180 degrees, even though each of its bonds is polar. The symmetry cancels the pulls. Remember that beautiful contradiction. Let us drill the neat way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion: the bond angle of water is smaller than that of ammonia. Reason: water has 2 lone pairs, while ammonia has only 1. Think like Sarah. Check each statement, then check the link. Is the assertion true? Yes, water bends more tightly. Is the reason true? Yes. And does the reason explain the assertion? Perfectly. The extra lone pair in water is exactly why its angle is smaller. Both true. Reason explains. Option A. Second one, assertion: carbon dioxide is a non-polar molecule. Reason: carbon dioxide has polar carbon-oxygen bonds. Both statements are true, no doubt. But pause. Does the second explain the first? No. Carbon dioxide is non-polar not because of the bonds, but in spite of them. Its linear symmetry makes the 2 equal poles cancel exactly. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every time. Third one, assertion: The shape of the sulfur hexafluoride molecule is octahedral. Reason: the central sulfur atom has one lone pair. Check the assertion first. Yes, sulfur hexafluoride is octahedral. Now the reason: is there a lone pair on sulfur? No, there is none at all. All 6 pairs are bonded. The assertion is true. The reason is false. Option C. A quick match now. Say each shape aloud before I reveal it. Methane matches with tetrahedral at 109.5 degrees, 4 bonds, no lone pairs. Ammonia matches with pyramidal at 107 degrees, 3 bonds and 1 lone pair pressing down. Boron trifluoride matches with trigonal planar at 120 degrees, a flat, tidy triangle. And xenon tetrafluoride matches with square planar at 90 degrees, 4 bonds and 2 lone pairs sitting opposite each other. If all 4 came to you before the reveal, the shapes are becoming yours. Here's a favorite new NEET format. I will read some statements. You silently count how many are correct. Statement 1. Water has a smaller bond angle than methane. Hold your verdict. Statement 2. Boron trifluoride is pyramidal. Picture that flat triangle before you decide. Statement 3. In VSEPR, the lone pair on lone pair repulsion is the strongest of them all. So, how many are correct? 2 are correct. Statements 1 and 3. Water truly bends tighter than methane because of its lone pairs, and lone pair on lone pair repulsion truly is the strongest. But statement 2 false. Boron trifluoride is not pyramidal at all. It is trigonal planar, flat as a sheet. 2 correct, 1 and 3. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. Geometry and shape are just 2 words for the same thing. It sounds harmless enough. But here is the truth. Shape counts only the bonded atoms, while geometry counts every electron domain. Lone pairs change the shape of a molecule without changing its underlying geometry. Ammonia and methane share a tetrahedral geometry, yet one is pyramidal and the other tetrahedral. Myth 2. Polar bonds always make a polar molecule. It feels obvious. Polar parts, polar whole, no? The truth: symmetry can quietly cancel the bond dipoles. Carbon dioxide has 2 polar bonds, yet because it is perfectly linear, the 2 poles point in opposite directions and cancel, leaving the whole molecule non-polar. Shape decides polarity, not the bonds alone. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No notes, just the ideas you built today. Question 1. What is the bond angle of water? Picture those 2 lone pairs squeezing. 104.5 degrees. Question 2. What is the shape of methane? 4 bonds, no lone pairs, tetrahedral. Question 3. Which repulsion is strongest in VSEPR? The lone pair on lone pair repulsion. Question 4. What is the shape of xenon tetrafluoride? 4 bonds and 2 lone pairs opposite each other, square planar. And question 5. The thinker. Why is carbon dioxide non-polar? Because its linear symmetry makes the 2 equal bond dipoles cancel exactly. If you caught that last one, you have truly understood today's class. Let us gather the whole class in one slow breath. Atoms bond to reach a stable octet, either by transferring electrons in ionic bond or by sharing them in a covalent bond. Lewis structures let us draw the electrons, and former charge picks the best structure, the one closest to 0. VSEPR is the master idea. Electron pairs repel and spread to maximum separation. The family of shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And lone pairs shrink the angles. Methane at 109.5 degrees, greater than ammonia at 107 degrees, greater than water at 104.5 degrees. And next class, we go deeper into the bond itself. Chemical bonding 2, valence bond theory and hybridization, the sp, sp2, and sp3 orbitals that give these shapes their true origin. Do not miss it. And so, my friend, you have just built the foundation of the single most asked chapter in all of NEET chemistry. Look at how far one simple idea carried you. Atoms seeking a stable octet, electron pairs refusing to crowd, lone pairs quietly bending the shape. Water is bent, ammonia is pyramidal, methane is a perfect tetrahedron. And now you do not memorize these, you understand them. Sarah, David, Lisa, and John all began exactly where you are right now with this one class. Be patient with yourself. Tonight, redraw the three shapes once, slowly, and let the shrinking angles settle into your memory. One idea at a time, you will crack NEET. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in the world of hybridization.